Thank you very much, Edward. It's my pleasure to give the talk to everybody this morning. I hope you can hear me relatively loud and clearly, and I'll try to keep my pace at an appropriate pace because I know it can be quite easy to get carried away and talk quite fast at the moment on these online sessions. So yes, as Edward mentioned, today I wanted to give a talk, a presentation on a subject that is quite close to my own heart, and I'll comment on that about that in a moment, but it's regarding intelligent conversational interfaces. And this is relevant and it is close to my own heart because indeed, I just give some background here to put this in context. I did my own PhD many moons ago, I suppose at this stage, over in Germany, originally looking at spoken human-robot interaction was the main subject of my PhD. And I suppose, as many students do, post a PhD, you can back away from an area a little bit, maybe because you're just so tired of an area. But also at the time, it was very difficult to do spoken interaction or even non-spoken dialogue style research because the machine learning methods weren't really there to do a decent job of the task. Now, fortunately, in the past 5, 6, 7 years, as you would all know, machine learning methods, and in particular deep learning methods, have really opened up many, many avenues for different areas of research. But one area in particular that's benefited dramatically from deep learning methods is the whole topic of what some people might call dialogue systems, other people call conversational agents. There's many terms that are used for this. But what we're talking about here is really the idea of some sort of agent that we're communicating with in a real or a virtual environment. It might be spoken, it might be text-based, it really doesn't matter, but we're trying to perform some sort of task. So what I would like to do in today's presentation is really give a little bit of a primer to people on some of the topics that are relevant in and around intelligent conversational agents. So I'd like to mention a little bit about where we are, where we've come from, the common technologies that in some cases are quite old that are still being applied to this area. But importantly, also give you an idea of the real state-of-the-art methods that are being applied into this area. Many of them you may be familiar with already, issues like embeddings, reinforcement learning, etc. But I'd like to give an indication of how these different techniques come together and where future directions may be heading. So I suppose in that context, this will be a little bit of a broad introduction rather than what we might call a very deep dive on a specific topic. But maybe indeed, if Edward is scheduling a 4th or a 5th session of these seminars, depending on how COVID goes, I can always come back and do a little bit more of a deep dive on one aspect of what I'm going to talk about here today. So, in terms of where we are today, this bit of the conversation is now usually easy for me because I can point to practically everybody's home on this call and show how we have conversational systems and intelligent conversational systems already deployed, already being put to use. And as you know, they tend to work relatively well for certain specific tasks, setting timers, playing music, etc. And the fact that these work now isn't itself a minor miracle, because if you had looked at the same technology 10 years ago, without the advances that deep learning have brought to, say, speech recognition, there was no possibility of these techniques really working, even in a semi-robust way. Now, that said, I do appreciate that many people with accents, etc., still find interaction with these systems tough, but generally they're getting better. So obviously there's the big players, there are derivative systems from those big players, and indeed there have been failures along the way. But by and large, this sort of technology is very much coming in and becoming a regular part of our daily lives. Now, of course, while those first smart speakers, so to speak, are hardware technologies, what is really underlying them tend to be very complicated architectures. Sometimes we give these things very nice, sexy names like Alexa and Siri and Google Assistant and all the offerings from others. But fundamentally, they're very large, deep, integrated AI systems that have a number of different technological components coming together to allow us to pose what are often vague queries to a system and get a relatively smart attempt at a reply. Now, don't get me wrong, it often makes a mess of it. These things are improving, but again, much better than where we were, say, 5 or 10 years ago. So those integrations, of course, are going a lot further than just smart speakers in the home. We are seeing the likes of Google Home and Alexa make their way into everything from televisions to watches to cars. And really, the opportunities for integration are quite endless. If you've got a smart device, you can easily deploy one of these systems into that smart device and interface and piggyback it into your systems, which is quite exciting in a way for any technology development companies. Of course, though, for many people on this call, a much more practical and a much more day-to-day application of these types of technologies that actually concern your business interests would be the application of smart, intelligent interfaces to customer support applications and the like. So this is typically the sort of application where normally a call center type environment might be used to process queries from users, be that over the phone or be that through some sort of chat interface on a website. But in either case, there are a lot of basic, simple queries that tend to be processed by human agents, and an awful lot of this can be automated and has been automated for many years. So for most companies, the big application of conversational agents, intelligent or otherwise, tend to be on these customer support application platforms. And of course, what these platforms look like can be quite varied. They can work well. They don't necessarily have to work well. Sometimes companies throw together very basic implementations and feel they've done a decent job, but we can really see differences when we look at some applications from the likes of IKEA, who have invested a fair amount of money in this sort of platform, versus other companies who deploy very much an off-the-shelf solution and then maybe get a little bit surprised that the capabilities of the system aren't quite what they had in mind. So underlying all of these customer support applications tend to be a set of frameworks from different companies, many of which are the big multinationals. IBM is obviously famous for its Watson platform. Amazon is there with their web services platform. There are many different companies offering solutions that aim to integrate basic, smart, conversational, intelligent interfaces together. And the reality is that many of these platforms do a decent enough job. Once you have the expertise to integrate with these platforms, the reality is a lot of the processing can be done on the servers from the service providers. And in the great scheme of things, and obviously you can argue about this particularly with respect to costs, but in the great scheme of things, these solutions tend to be approaching free in terms of their deployment. They're really cheap to deploy in the great scheme of things. The challenging aspect tends to be customizing them, tends to be implementing them for your own particular domain and training and fine-tuning them for your domain. That's where the big challenges really tend to be. So those services are there, and later in the talk I'll mention a little bit about other options, because you don't have to use those online services that are provided by, be them SMEs or multinationals. There are other ways in which this can be done, but I'll come back to that later in the talk. What I wanted to touch on first was maybe go beyond that, say, where are we going in terms of more intelligent applications? And really the state of the art very much still is in two domains, and big applications in two domains. One is robotics, and robotics still is a major interest, particularly with an aging population, where we have elderly people who need to be cared for. And particularly in a COVID dynamic, this idea of having agents be them robots or semi-robots interacting with people in a hospital setting, actually starts to become quite appealing if we can limit disease vectors and attack vectors for COVID and other potential flus in the future coming in. So the robotic area for elder care and hospital care is major. And another area that's also very, very important to us in the dialogue community is online tutorials, online education. Now, I'm not talking necessarily about replacing the universities here. We're talking about things like language tutorials, mathematics tutorials, giving students extra tuition where they're being guided through a process. That's very expensive for schools, universities, and other educational institutes to provide. And many companies are looking to invest in this area because they really see that artificial agent delivery of certain content as being very valuable. So later in the talk, I'll come back to some of the technologies that we're investigating that are really aimed at addressing this sort of hot topic area. Now, of course, as anybody here on this talk would hopefully know, the idea of conversational agents are very, very far from new. Anyone who knows the area at all will know that ELIZA is probably one of the oldest, is the oldest conversational agent really, and dates back to the 60s. And fundamentally, while ELIZA was well known as sort of a therapeutic agent, somebody you could have basic conversations with and would ask you how you feel, etc. Fundamentally, superficially, when you look at many current applications, including in the area of psychological therapeutics based on agents, the behavior of these systems seems to be quite similar. But of course, the technologies and the abilities underpinning what we have now is a vast improvement on what was back there. So in terms of getting a little bit deeper into what conversational agents provide, I think it's useful just for a minute or two to ground people in what is the common anatomy of a conversational interface. And just to remind everybody that when I say conversational, I'm not necessarily talking about spoken interface. Yes, spoken interface can be one of the modalities that we're talking about, but conversational interfaces will often include text-based. The important point is that we're interacting via language. So the common anatomy of such a system usually boils down to 4 components. We have some sort of input processing where we're taking the language provided by a user. It could be speech, it could be text, and we're performing some sort of analysis on it. And that analysis is usually trying to extract some element of semantic meaning from the text. We then perform a job of language understanding. Now, language understanding is a little bit different to just processing the input, because language understanding tends to be about taking the input and putting it in a context. So what does the user's language mean in the current context? And that context could be spatial, what's the physical environment of the user? That context could be linguistic. What else has the user said, or has the agent said to the user, etc. And that contextualization, that understanding, by far is the most complicated aspect of building a conversational interface. The third element of a conversational interface tends to be response planning. In other words, deciding what we as an agent will do next in response to what a user said, or in response indeed to changes in the environment. That's not necessarily deciding on the exact words we're going to use, but just the gist, the strategy of what will we do next. And then of course, the final step is output production, where we go from some sort of instruction set saying what we would like to achieve, and we figure out what is an appropriate structuring of language, what are the intonations we should use, what are the gestures we should use to get this information back to the user. Now, for those who work in the area, the 2 elements here on the right, language understanding and response planning, tend to be grouped together and referred to as dialogue management in general. And you'll see lots of references, not just in research, but in systems development, from the big providers that I mentioned earlier, talking about the dialogue manager. And so this is what the dialogue manager is doing. It's taking user utterances, putting them in a context, and deciding what to say next. Now, for any given deployment of a conversational interface, there will tend to be a slightly different configuration of systems and components. And the reality is the number of different configurations that can be used and strung together for a particular application is vast, right? So we can't enumerate them all, but the general gist of these four flowing stages still holds. So for example, if we had, as I have here, something like a chat agent being based on a website that's processing basic user FAQ type queries, we might have a setup like this, where we're taking language, we're performing your basic, what I would refer to as basic text work, like tokenization, normalization of the text, and then we're going on to processes like entity extraction, updating the dialogue state, etc., and just going back through the whole process. So I won't enumerate all of these. That's not the point. The point is to say, well, there are many different components, there are many different types of natural language processing and machine learning that we do need to integrate in together for these types of systems. So that's your basic anatomy of a conversational agent. And I think today I'm mostly talking about these first two steps: the actual input processing and language understanding. The generation of responses, etc., is in itself something I could easily do a talk or two about. So we'll stay focused on the input side today. So also, as I mentioned, if we're dealing with text, there's one issue, but if you want a speech-based interface, it's in many ways essentially the same components, except we need speech recognition at the front end. We need text-to-speech at the front end as well, but to go back to the user, it's not significantly different. However, we still need to perform tasks like tokenization, analysis, and putting the language in context. The only difference is we need to figure out what words the sound signal might correspond to. So if they are the components of an intelligent conversational interface, one question I often get asked by companies and indeed research students, etc., is what are the differences between the many different types of conversational systems we tend to see either being marketed or demonstrated in newspapers, etc., because it's quite easy to make something that looks intelligent but isn't intelligent. So I might refer to it as a sort of a dumb intelligence. And I think it's important that we as researchers or developers or systems integrators have a very good understanding of the different types of intelligence that come into play for these types of systems. So with that in mind, I just thought it might be useful to give my perspective on this. And how I would initially describe it to people is to think about sort of a conversational spectrum, where at one end we have chatbots. Chatbots, also referred to as chit-chat type agents, tend to be very superficial. So these are the types of systems like Eliza that can respond to something that you said with a response that is superficially intelligent sounding. So you say, oh, I'm not feeling so well. And Eliza says, oh, that's terrible. Tell me about it. Superficially, that sounds really intelligent. But the reality is it tends to be based on very hard-coded rules where the system isn't actually learning or understanding anything about you. So there's no real model of the user being built up. There's certainly no model of the task being built up. And these are the oldest forms of conversational agents, but they're still, and this is the bit that makes me fairly sad, they are still the ones that the newspapers tend to report on the most aggressively because they look intelligent. Now, at the other end of this spectrum, I would have what I refer to as task-driven dialogue systems. Now, task-driven dialogue systems, they're your more classical system for booking an airline flight or booking a restaurant or maybe trying to perform interactions with a bank regarding your bank account. These systems don't have the same elegant conversational flow as your chit-chat based systems, and they'll be usually fairly targeted in trying to achieve a goal, a task. And how they do this can vary a little bit. They can follow very concrete and hard-coded finite state machine type structures, or more commonly, they're usually designed in terms of having some sort of frame of information that's required. And then the system itself has a meta algorithm around that that is continuously gathering the information that the user has provided to fill in that frame, or indeed asking the user for the bits of information that are needed. These systems typically are building a model of what the user has said. They understand more about what the user has said, but users don't tend to find them as much fun because, well, being blunt, they're not as much fun. They're designed for getting the task done. The reality, of course, is it's a spectrum from one end to the other. And in fact, I'd argue that it's more than just a spectrum. If we really want to dig down and look at the different offerings, look at the different types of systems that are commonly deployed, you could map these across many different dimensions. You'll have to forgive me as an academic, I can't resist sort of boiling things down across dimensions, but we can look at different conversational systems as varying in their conversational ability, which I have down along the bottom, along the x-axis there, or indeed on their task focus, which I have along the y-axis here. So if we just take a few of these and have a look at them, what I mean is that down at the bottom left, we have something like those chit chat or those chatbot type agents that I mentioned. Their conversational ability, it's quite simplistic. They're just doing what are called stimulus response questions and answers. Hi, goodbye, that sort of thing. And they're not very focused on the task. People like them, but they're fairly basic. Sort of moving up into really task-focused area, you have these sorts of finite state machine-based systems that are very much focused on performing a task, but the structure of the conversation we can have between the user and the system tends to be quite hard-coded. So they can do a job, but they're very, very, very far from being naturalistic. Then the third big class of these systems, I would say, is the sort of the agent-based type systems, where we explicitly define what sort of information the system needs to gather, but we have outer algorithms that have been trained, etc., to gather that information back together for the user. Now, just as I note here, I suppose in this diagram, there are many different types of terminology that are used. So another big one that I haven't mentioned so far is IVR systems, interactive voice response. I suppose for about 10 years, that was the big buzz term in the area, but yeah, I tend to think people shouldn't get hung up on the particular type or name of the technology they're looking at. They really need to think about what level of intelligence do they want to appear to have, and how task focused is their particular goal of an application. Okay, so that is sort of what I would call a little bit of a broad view of what are the different types of systems and what are an overview of the components. In order to dive a little bit deeper into the systems, it's important to try to understand what people are trying to achieve with language when they're interacting with a system like this. And the reality is, while we mightn't think of this consciously because we're smart, language is a very complicated thing to process and to deal with. And there are very good reasons why this is the case. So language is a very slow and serialized form of communication. Like if you think about it in terms of words, how much information can we really convey in a 10-second sentence? It's not much. So in order for we as humans to have evolved and successfully communicate via language, this slow serialized form of communication, we have evolved an ability to apply an awful lot of context in order to allow us to use ambiguities in our language, in order to allow us to leave a lot of information out of what we're saying. And we have the ability, based on our understanding of context, our understanding of background knowledge, to reconstruct really what the user meant. And that's a common expression we use in natural language processing, the difference between what is said and what is the meaning, or what is the intent. It's easy for us to do this as humans. It's incredibly difficult for computer systems to do this. Now, fortunately, for most practical tasks that we want to perform with intelligent conversational systems, users are quite nice in that they tend to be relatively explicit and literal with their language, which is great because we can sort of make certain assumptions about how users will interact with the systems. It does make the job of prototyping systems easier. It certainly doesn't make it straightforward to do. And so in the next couple of slides, I'd just like to highlight the sort of tasks that we have to perform in extracting information from what the user says, and then have a little look at some of the technologies that we apply in that process. So in terms of building intelligent conversational systems, the first most important job we need to be able to do is a task of entity extraction. Okay, and what that basically means is looking at the content of individual sentence and figuring out what things, what items that the user is really talking about. And in practice, when we're building these systems, that means gathering huge corpora of interactions between maybe a user and a customer service agent and labeling these corpora in terms of what are the entities that are being expressed. In very simple cases, if for example, we're building a system to interact with users in a banking situation, the number of different types of entities might be very, very simple, as I have here in the first couple of sentences. You know, we talk about accounts, we talk about Visa, we talk maybe about different branches, but in the great scheme of things, it's not an awful lot of different entity types. So that tends to be relatively straightforward in a given domain. However, it can get more complicated if, for example, on the final sentence, we have multiple entities being discussed in an individual sentence. We need to be able to extract all of those entities and be fairly sure of our probabilities for them. We can also have to deal, obviously, with the inevitable ambiguities. Like if we're really to worry, for the sake of worry, we can always find ambiguities to worry about. The classic example in this context, I suppose, is a bank. Is a bank a corporate entity, or is a bank a branch, or is a bank the side of a river? They're those classical ambiguities that I suppose for years people tended to worry about quite a bit. But if you're building a very concrete application, such as a customer service application, to be honest, we can usually stick our fingers in our ears, so to speak, and ignore those sorts of ambiguities. And they'll only really come into play as we try to build more wide systems that can deal with multiple domains in parallel. So job one is the entity extraction. Job two, and arguably a harder job, is what's called intent recognition. Intent recognition goes a little bit further than entity extraction in that we're trying to figure out what the user is aiming to achieve with their language. Again, this tends to be a little bit easier in a very focused domain, but in general, it's not always as easy as you might think. And a big challenge in building conversational agents is a very practical one of building and getting these data sets that I mentioned and actually labeling them for intents. I have a good friend who worked for IBM on the Watson platform for many, many years, and he notes often, and he does some nice online videos about this, how intent recognition in, when they're actually designing solutions to be integrated into Watson, a team of people can spend 5 to 10 minutes sitting down, looking at a sentence from a corpus and trying to decide what is the intent that is meant here. So it can be quite complex, quite expensive, particularly if the intents and how users express things tends to be a little vague. Now, the good news is, by and large, users in these domains are well behaved. So we can look at our structure of language and see very nice pairings that we can use, users asking queries, a system or human agent giving back an answer. Language tends to be at a fine grain, quite well structured, quite simple. And your basic intelligent conversational systems can be based around this idea. So we can have simple interaction pairs. And if we apply this sort of technique, we can maybe build very simple agents for question answering against an FAQ. So these are so-called FAQ bots in a very fast way, and we can prototype systems quite quickly for it. However, if we look at the end sentence there, like I'd like to book a table for 2 in McSharry's tonight, that's a little bit more complicated, and we tend to go down a slightly different route for that. And that was this idea of frames and slots that I mentioned earlier. And a good conversational agent is going to want to be able to deal with these more complex queries from users in multiple ways. Either to be able to take the information directly from the user if they compose a nice single sentence together, or more importantly, have a well-structured conversation with the agent to extract that information. So this is your core, good old-fashioned approach to conversational agents. It's about entity extraction, it's about intent recognition. And the good news is that the NLP techniques for these sorts of activities have existed for many years. And fundamentally, the types of dialogue systems that Watson and other systems deploy for these applications are straightforward and based on technology that's 10 to 15 years old. They work well. They might be a little bit rigid. They might need maybe a lot of labeling of data, but generally they do work quite well. And things like good old-fashioned parts of speech tagging, named entity recognition are all pulled together to make those solutions work fantastic. What I wanted to step on to talk about a little bit more, however, was where more modern state-of-the-art techniques tend to come into play for these sorts of systems. So in modern systems, we don't want just to use good old-fashioned natural language processing. It does a job, it does a certain job, but where it starts to fall down is when users use language that we didn't expect, or users use language that's slightly different to what we trained for. Good old-fashioned techniques don't deal well with that by and large, but one set of techniques that deal incredibly well with it is the idea of natural language embeddings. Now, I did have a quick look at the last couple of presentations that were given, and I noticed that not much had been done on embeddings. So this is going to be my whirlwind 2 to 3 minute reminder of people what embeddings are. So just as a reminder, we need to be able to represent text. We need to represent what the user said. Now, there is no fantastic, perfect way for representing text. If you're used to designing computer programs, you know that a string in a programming language just captures in a very fixed way the byte sequence that corresponds to characters. And it works relatively well for storing text, but it's absolutely useless when we want to do anything intelligent with the text. We need something that gives us more information on what the user said rather than just a representation of what the user said. So the classic approach to representing text is what's called bag of words. In bag of words, basically we take our whole vocabulary and we say that for every word in our dictionary, in our vocabulary, we have a feature. And that feature is true, is a 1, if that word was present in our input sentence, and it's a 0 otherwise. And we can generally do this, with a different row per word, or better still, we can maybe have a sort of a bag of words approach where our entire sentence is represented with 1 row. And if a word was present in the sentence, a particular cell along that row will be given a true or a 1. So bag of words are great, but they have a number of limitations. Bag of words lose the order of words themselves. The vectors that represent sentences are really long because they're basically as long as our dictionaries, which can be quite long. And importantly, the similarity between words is lost. The way a bag of words representation works, there is the same distance, the same difference in meaning between dog and devil as there is between dog and puppy. They both are as equally far away from each other in the representation. So has happened over many years is there have been different approaches to representation and meaning. And the most important of these, and the one that's relevant to us here today, is the idea of the distributed representations. And what happens with a distributed representation is that instead of having a very basic approach where each word only corresponds to one feature in our representation, instead, each word is basically positioned in a place in space. Now, for the sake of our discussion here, you can think about space as being three-dimensional, and basically what we are saying is that the word dog is given a place in our three-dimensional representation, and you know what? The word puppy is also given a place in the three-dimensional representation, but it's really close to dog. And similarly, the word Labrador is given a place in the three-dimensional representation, but it's also quite close to dog and puppy, whereas the word for devil or the word for table, etc., are much further away in this three-dimensional representation. So each word is represented as a vector of real numbers. Now in practice, the number of dimensions in this representation is much, much bigger than 3. It can be something like 128 dimensions, and it's a nice way of capturing the meaning of words. And we commonly refer to this as distributed representations. And what's very nice, and this is old research, this is basic stuff that most of you will know, but just for anyone who doesn't know it, what we can do then is look at these representations that we build up for words. And if we flatten them out and have a look, what's really important is when we build these representations automatically, words that have similar meanings tend to co-occur in the space. So words about places tend to live together in a clump. Words about colors tend to live together in a clump. And this is really useful to us because it means that our representation that we can automatically construct at its core has an essence of meaning built into it. So this is just a sort of a zoom in on some of those areas just to illustrate that in that big clump of words, if we zoom in, we will see things that have similar meanings all gathered together. That's just making my point. So word embeddings are pretty well known, pretty well understood at this stage, and indeed to a great extent we have replaced them with so-called sentence embeddings. So the big difference between sentence embeddings and word embeddings is quite simply an issue of granularity. So with word embeddings on the top right here, every word is represented as an individual point of space in our high dimensional space, whereas in a sentence embedding down here at the bottom left, individual sentences are given representations in space. Now, today, I don't at all have time to go into detail on how we construct these sorts of models. How are they built? That would be a topic for another conversation. But importantly for us, what we can see is that for these sentence embeddings, again, we have this same phenomenon where sentences or user utterances with similar meaning are clumped together in this sentence representation space. And that's really important to us. It's really, really useful. Because what it allows us to do is something like this. We can do some nice, very simple, not fancy, very simple maths and compare the distances of the representations of different sentences in our space. And what I've got here is basically a correlate, it's a distance matrix. It's asking how far away is each sentence from each other. And with a very basic approach to distances and how close are sentences to each other, we can see that this sort of approach will say that statements like, can I check the limit on my credit card? What's the max on my Visa? What is the, sorry, oh yeah, I purposely did spelling mistakes here. What is the max on my Visa? Will all have very similar meanings. They will be clumped together. Whereas you can see the next block of 4 are all sort of not as tightly bound together, but they're still pretty close. I need to take a mortgage break. Can I take a break in my mortgage, etc., are fairly strong and related to each other. Of course, these approaches aren't perfect. And I show there with the 7th example down, can I get a loan for a holiday? You know, semantically and superficially, that's quite similar in meaning as far as this system is concerned to something like, can I take a break on my mortgage? So it's saying it's quite similar in meaning. So I guess what I want to emphasize here is this sort of approach to using sentence embeddings isn't foolproof. It's just another piece of technology we want to use in our arsenal of constructing intelligent systems. So why do I say all of this? I say all of this because this approach to using embeddings, what are called sentence embeddings, or indeed sort of state-of-the-art conversational embeddings, allows us to take what are simple, more old-fashioned systems based on entity recognition and intent recognition that I highlighted earlier, and add to them, not replace necessarily, but add to them more generalized rules on these sorts of document distances or sentence distances, which means that even if our main really fact-based extraction process fails, that we can have a more robust, more generalized, more intelligent extra system that can be fallen back to and really give us more confidence in what we're saying back to our users. And that's really an important point at where state-of-the-art development is at the moment. So I promised to go back to the issue of tools and toolkits. So as mentioned earlier, yeah, there are many service providers who are in this domain who can provide systems quickly enough. You know, using Amazon or AWS or Microsoft system, you can develop and deploy applications for free at first, you know, subject to a couple of thousand users using them, and really have a good feeling of what the standard commercial toolkits can provide. If, however, you're more into actually experimenting and understanding what's going on under the hood, the good news is there are tools nowadays that can be used to help you in that way. And one that I think is particularly useful, and one that I like an awful lot, is RASA. It's a toolkit for the integration of conversational systems. And being blunt, I wish this existed when I was doing my PhD, because it allows people to really build up intelligent software very quickly and then experiment with their own components, deploying it on their own servers, etc., without having to go the way of the big multinationals, which, depending on where you want to deploy, etc., and depending on any GDPR issues, can be really, really beneficial, really, really useful. And I'm not involved in RASA, I just like to use it, but one very important point to highlight is it really does include state-of-the-art methods, not just good old-fashioned simple methods, but everything's there in terms of conversational embeddings, etc. And it's free and open source, running TensorFlow under the hood for people to make use of. Now, I just want to note, though, that in as much as a toolkit like this is useful, toolkits like this, or deploying on Amazon type services, are still dependent fundamentally on having data to train a system, data to construct a system. So if we just take RASA as an example, you're still going to have to sit down and define lots of examples of what users said, define what they meant by them, define their intents. That all still needs to be done. And being blunt, it requires a lot of data. So really, the first point in any sort of system development is sitting down and getting access to data and starting to annotate that data, lots and lots of data. And inevitably, and let's not kid ourselves, gathering this sort of data is costly. It is costly to gather it, because usually you need some sort of deployment already where users are talking to, you know, maybe human agents that you employ, and, you know, giving their queries to the system. But it's not just gathering the data, it's the annotation afterwards that can be quite costly. And really you need experts in the area to help with that intent recognition process and so forth. Yeah, I sort of just highlighted that process here in this slide, saying it is about getting the data, iterating through the data to make the labelings, training your systems, deploying them, and really having that sort of agile cycle for system development in the area. Now, that's all very practical day-to-day if you really want to deploy these systems type points. just for the last 5 minutes, because I want to give myself time to take some questions, I just wanted to highlight some of what I see as the next generation issues. Now, they're next generation with respect to day-to-day deployment, but they'd be very much what the research side of things are looking at the moment. So the first thing to point out is, if we look back at my original sort of spectrum of chatbots down to task-driven dialogue systems, these are the extremes. And where we are really trying to target in terms of sophisticated system development is really this center ground sweet spot, where interactions are quite relaxed and conversational, but where we're still trying to target some type of task domain. And the big examples of these sorts of sweet spot type conversational structures, they are the robots that I mentioned at the start. They are the dialogue agents, the tutorial agents that I mentioned at the start. Those systems, they're not happy just to be chatbots. They're not happy to do very boring task-driven dialogue. They need this sort of middle ground where the system is still driving the conversation with a goal in mind, but able to deal with that conversation in a much more flexible way. And to achieve those sorts of goals, the research community, and I've pulled a few areas just from the research community to mention to you here, are doing some incredibly interesting work. One issue that I highlight that I think is really important are things like conversational multimodal question answering, where we're looking at taking that representation of what the user said, taking the representation of the game or what the user sees or what the system sees, and being able to combine that information in nice multimodal ways to do things like question answering. That's really important. That's at the state-of-the-art level. The other issue that's at the state of the art is, of course, using end-to-end system training. Do we want to train all these individual components by themselves, as we tend to do at the moment, or is our ultimate goal to build really complex systems through what's called end-to-end training? In other words, I just need a single data set and I build the whole system from scratch. Encoder-decoder architectures give us a starting point for this, but certainly not the end point. Another big area, and I'm almost finished, right? But another big area for research at the moment, which I think is very important to many people on this call maybe, is that integration of the conversational system with things like knowledge graphs, things like the representations that major companies have built up of their own organizational information, so that this information can be both queried and, importantly, updated by the user on the basis of extra information coming in. So that's another hot topic that I think is worth addressing. And finally, one topic that's very important and very popular for many is using reinforcement learning for fine-tuning these systems. So the idea is we can either use reinforcement learning in a simulated way when we're first training our systems, or equally importantly, when we deploy them out to the real world, what we've basically got is a reinforcement learning scenario. The system is doing things with the users, sometimes getting it right, sometimes getting it wrong, and we need to be able to feed that information back into the system, update the rules online and in a way that's smooth and elegant to the user. So on that note, I think I'll wind up there. As I mentioned, this was very much just sort of a quick stop guide to issues around conversational intelligence systems. I'm happy to answer any questions either now, or if people have questions that they want to drop a line to me afterwards, that would be great. And if people have an appetite for this, I'd certainly be happy to deep dive on any of these topics in the future. Thanks a million.